Hello and welcome to my presentation. I'm Nicolas Villela from the University of Bern, and today I will present how you can do a double spike calibration. Now I will start by explaining this diagram in details because it is crucial to understand it in order to understand the double spike calibration. I will start by walking you through it step by step. Now first, let's say that we have a melt plotting here in our 3D isotopic space, and we produce a mineral from it. This mineral will fractionate isotopes, and this blue fractionation path can actually be described by this exponential fractionation law that we have on the right. This p-value that you have in this equation is actually a constant, and you don't need to worry about it for the rest of the talk. Now, a few million years later, we have a geologist that appears and takes a sample from this mineral. Now, if he wants to trace back what this fractionation was from the melt, he will have a hard time because usually this path is lost in nature. So he needs to find another idea, and what he remembers is that he has a standard in his lab. Theoretically, what he could do is calculate what this fractionation path would be if he were to produce this mineral from his standard. This is something he can do with the very same equation that we saw earlier. Now, the ultimate goal of the double spike method is to obtain this alpha value in order to directly obtain your delta value, which you can publish in papers. This is the equation that links these two values. The next step is to take your sample and mix it with a double spike. What you will create will be somewhere along this mixing line. You will create this mixture. This equation on the right describes a mixture where you have your mixture M on the right side of the equation, which is equal to your first part being the standard, your second part being your double spike, and you mix them together according to this lambda factor. It is important to remember that all mixtures that you create will lie somewhere along this mixing line. You will not be able to create a mixture that is apart from this mixing line. This is important because it will be used in our double spike calibration. What we will do next is that we will introduce our mixture into a mass spectrometer in order to get our isotopic composition. In the machine, there is some more fractionation happening, which will follow this path. And finally, this is the value that you will measure. This path again can be described by the exponential fractionation law. So we will change our expression and introduce this expression here. We will do the same with our natural fractionation, and this is how we will receive our double spike equation. Now, if you look at it carefully, you will notice that we actually have vectors in this equation. Now you can look at your double spike, your standard composition, and your measurement as being points in a 3D space, and therefore having 3 coordinates. So this means that we actually have 3 equations. This looks scary at first, but it is actually what saves us. Because if we look at the amount of unknowns, we have our beta value, which is the fractionation happening in the machine, which we don't know. We also have natural fractionation, which is the value we want to solve the equation for. And we have our lambda value, which is unknown. So we don't know the exact proportions in which we mixed our sample with the double spike. So we have 3 equations and we have 3 unknowns. This means that we can solve this equation system. When you come to a university and calibrations have already been done, this is the situation that you will encounter. You will have your double spike composition, which is known, your standard composition, which is known. You will perform your measurements and you will solve the equation to get your unknowns. In a case where you want to establish a new method, you don't know your double spike composition initially, and you don't know your standard composition. So if you were to measure your samples, you will not be able to solve this equation. Now the first part will be to determine our standard composition. So what you can do is choose a standard that has been already measured very precisely, or you can set your standard to a 0 value. So this will solve our first part of the problem. We'll now know our standard composition. Next will be to determine our double spike composition. this is where the calibration part starts. So initially, when you order a double spike, you will have a rough estimate of the double spike composition. But if you were to use this rough estimate in your equations, you will actually end up with a huge range where your mixing line could lie, and this will result in a huge error. So this is a bad thing that no one should do. So we will now change our double spike equation so that we can solve it in a different way. So remember, we have our two parts in our mixing equation. Now the problem is that we don't know our first part, so we'll get rid of it and we'll introduce a unknown vector. So we'll say that our mixture can be described by our standard plus a unknown vector. Now we'll say that this vector is a scalar times a unit vector. A unit vector is a vector that has the length 1 and only carries directional information. In spherical coordinates, this is how our unit vector would look like. It is fully described by two angles being theta and phi. So remember, this vector over here looks complicated, but is actually a vector that gives us a direction and has the length 1. And we multiply or stretch this vector by the factor mu. So this is how our new double spike equation looks now. We have introduced new unknowns being theta, phi, and mu. Now in our 3D isotopic space, this equation actually describes the following. So we have our mixture that we measure at this point, which got fractionated along this path. Eventually we reach this point that we can reach if we start at our standard composition over here and go along this direction that is given by our unit vector, and we go along this path for the amount of length that is defined by our factor mu. And eventually we reach the same point as from this path. If we look carefully at our double spike equation, we'll notice that we actually have 3 equations but 4 unknowns, so this system cannot be solved. What we will do next is that we will perform 2 individual measurements of different mixtures. So our first mixture will give us 3 equations, and our second mixture will give us 3 equations. In both cases, we will not know the fractionation that occurs during our measurement within the machine. We'll know our standard composition, we will know our measured value, but we will not know our unit vector, and we will not know how long we need to go into this direction in order to get to the same point. Now we actually have 6 equations and 6 unknowns, and what we want to do is solve this equation system in order to obtain our 2 angles theta and phi. This is what it looks like in 3D isotopic space. We have our 2 measurements that we project along our exponential fractionation path. Now remember that all mixtures we create have to be on a line. So we know that these mixtures have to be on a line that goes through our standard. So if we solve this equation system, we will obtain our unit vector pointing in direction of this mixing line. Now at this point we are actually finished with our calibration, as we know our 2 angles. From now on, these angles will remain always the same, as they point towards our double spike, and the composition of our double spike should not change. Now our equation has 3 unknowns and 3 equations, so we can solve it and obtain our alpha value. In our isotope space, from now on, when we perform measurements, we will have our measurement that we will project along this path to get to this point, which is this side of the equation, and we say that we can get to this point via the path on this side of the equation, where we start at our standard composition, go into the direction defined by our unit vector to eventually meet the same point. Now solving this equation will give us our alpha value, which then gives us our delta value, which we can publish. If you want to use the initial double spike composition, you can perform a second calibration towards a standard with a different isotopic composition. And using both unit vectors, you should be able to get the actual double spike composition, which then lets you solve this equation. Thank you for your attention. If you have any comments, leave them in the comments section below, and I will try to answer them. Bye bye.